Good afternoon, everyone. Um, I'll be posting this slide with voiceover there in case we are unable to meet because of the electricity situation in Yola for some days now. We discussed limit at infinity in our last class, and I gave you some work to do on that. So we'll just move on today to look at infinite limits, infinite limits. So if you have n greater than 0, the limit of this function 1 all over x minus a into n, as your x tends to a positive, is infinity. You can always experiment this. So if you pick any value a and then this n, the power a, is positive, not equal to 0, greater than 0. So you start substituting different values of x from the positive side of a. Then that limit, if it is the reciprocal of it, it will always tend to infinity. So you can experiment with any number. Let your a be 3. Okay. So as x tends to from the positive side of 3, start from 8, 7, 6, 5, 4, and it's coming down. For different value of x, as it's moving towards that 3a, we will say that the infinity as you take the reciprocal will be going to infinity. So this is an example of infinite limits. And you see the graph of this. You can use any utility to plot this, or you can also plot manually. Okay, so pick your a, say if n is 2 greater than 0, and then your a, say 4. So if you take this limit 1 all over x minus a, x minus 4 raised to the power of say 2. So compute for different a from the side of 4. This is your 0, this is your 4. So as you are coming from the right, 4 positive. Okay. So as your x tends to 4 positive. So 5, 6, 7, 8. And then take the reciprocal. With your calculator, you will see that your solution is moving to infinity. So please note this standard, and this works only for n equals to when n is greater than 0. So that is for a positive. Then we also have this expression for a negative. For a negative, don't forget that your n is greater than 0. But from the right side of a and from the left hand side of a, your solution is the same. So the limit exists for all n greater than 0. And you see the graph, you can always experiment. Then when you take the limit, when n is odd, please note this is when n is even and is greater than 0. But when n is odd, so we have minus infinity. When n is even, you have positive infinity. But when your n is odd, for negative, please, a negative from the left. Whether n is odd or even, for a positive, it is infinity. But when n is odd, from the left of a, it is positive even, but it is negative when it is odd from the negative side of a. So please note the difference between these two formulas so that you know when you say the infinite limit is infinity for odd n and for even n. And you have the graph there. So for example, find the limit of this as x tends to the zero positive from the zero side. Again, the same approach, divide with the ix power. So if we divide here by x raised to power 2, raised to power 2, raised to power 2, raised to power 2, that gives you this. Okay, so this will remain as 3, this will tend to infinity, this is also going to infinity, while 2 is 2. So at the end of the day, 3 plus infinity divided by 2 will still give you infinity. So these are examples of infinite limits. Infinite limits. Okay, simplify, and then you say that this again we from this is from the positive side of -3, this will give us minus infinity, and you have the graph if you're asked to sketch the graph. So general limits, we just touch a few limits under trigonometric functions. You remember your trig functions, and this again you can always experiment with your calculator by picking different values. So f of x is sin x and g of x is this. These are basic trig functions, and from these two trig functions, you can generate the other 4 functions: the tan function, the sine function, the cosine function, the cot function, the cosec function can be generated from these two. Okay, so this is your sine graph. I know all of you are familiar with the sine graph, and then this is your cosine graph. The amplitude is 1, okay, and the range is from -1 and 1, as you can see, and it has the period of 2 pi. From 0 to 2 pi you have 1 revolution. These are properties of the sine and cosine graph, and these are continuous graph from negative infinity to positive infinity, as the case may be. So we conclude that they are continuous function everywhere. So these are continuous function. You can see there is no point of discontinuity on both the sine and the cosine graph. So for sine and cosine graph, they are continuous everywhere. Okay, so the limit of sine x as x tends to a particular constant is equals to sine of that constant. Simply replace that constant, replace x with the constant and compute your, okay, and the same thing for cosine function too. We take the same thing for cosine function. So the tangent and secant functions are continuous everywhere in their domain. Continuous everywhere in their domain. And if you sketch the graph, notice what you have. So this is actually the domain. All x not equal to pi plus or minus pi over 2. Plus pi 2 pi, you have 3 pi over 2, and you continue like that. So any other x apart from this is actually the domain for tan x and sec x. Unlike the sine and cosine, where its own domain is minus infinity and positive infinity, meaning you can find any angle within this domain. But for tangent and secant, you have to be mindful of the domain. We've done this before, it's just a revision. So just one or two examples on trig limit of trig functions. Limit of sec x as x tends to pi all over 2 positive is negative infinity. You can confirm all this using your calculator. And from the length is positive infinity. Another example, x as x tends to minus 3 pi over 2 from the right of tangent function. This will give you minus infinity. So these are basic examples that you can substitute them to your calculator, and then you get the limit going to infinity. Or you use a table with different values coming from the left, from minus 3 pi over 2, reduce it, substitute, and you see the behavior of the function. So this is not different from what we've been doing. And you see that in this case, as you are coming from the left towards minus 3 pi over 2, in your table, your function will keep increasing and moving towards infinity. So this is the approach for all of this. For cut function is minus infinity as x tends to negative of pi, and then this is 1. So these are just different examples that you can look at for this. Now finally on this, before we move on to our main topic, limit and exponential functions. This is an exponential function. Y equals to x, y equals to a raised to power x. If your a is positive, sorry, a is greater than 1, not positive now. A must be greater than 1. Now if a is equals to 1, your answer will still be 1. 1 raised to power whatever x is. So but for a greater than 1, we have this exponential function, and this is the graph of it. So you can sketch this graph by putting different values. If your a is 2, put 1, put x is 1, x is 2, like that. You have this function. X can be anything. Okay. So, but when your a is between 0 and 1, this is a greater than 1. This is a between 0 and 1. So you have this. You have your graph. So the above graph confirms that exponential functions are also continuous everywhere. Everywhere. There is no point of discontinuity, and this is what we want you to note. Sine and cosine function, continuous everywhere. Tangent, secant, cotangent, and cosecant, they are continuous only within their domain. Whereas the exponential function, as we have it, is continuous everywhere. Okay, so limit again, how do you compute the limits? Limit of ax is an exponential function as x tends to a constant c. Simply substitute that c, it becomes ac, and evaluate it, whatever value of a raised to power c